Alright everybody, welcome back to our last video in this playlist on sequences in series, where we'll talk about that infinite case and what happens if our sequence doesn't ever end and if we take the sum of an infinite number of terms. This is essentially what we're going to get into here. There's a few definitions at the top here. Finite series, the ones that are going to stop, they terminate, they have an end term. Or the infinite series, which continue forever and will keep on increasing. And you can see that it doesn't end, which is what the ellipses tell us, those three dots there. We're going to talk about two terms, divergent or convergent, what they mean. And divergent means it's a sequence that doesn't approach a specific value. And really this is the basis of calculus and limits. When you think about, if we keep on talking about successive terms to infinity, what happens near that infinite point? And convergent, what happens when our sequence or our series approaches a specific value or a specific sum. So let's think about what happens with any given series, and if we look at 5 terms, 10 terms, 50 terms, what happens when you start to add things together. So think about that formula we built together over the past few videos. Really it's going to be the same one we're going to talk about. So our first term multiplied by our ratio n times minus 1 and then r minus 1. Again, this will give you the sum of the first n terms of a geometric series, but we're going to look at 5 terms specifically. So with the information we have, I know that t1 is 48. I know that the ratio here is also 1/3 because I can take 16, divide it by 48 to get our ratio. If you plug in what you know, so 48 is your first term, ratio of 1/3, n is 5, minus 1, underneath in your denominator, 1/3 minus 1. If you were to plug all that in your calculator, and I won't sit here and do it, I've got the numbers waiting for me, you end up with something really close to 71. Okay, 71.7037. 037. So you can try it on your devices. Make sure you get the same number. I know calculators can be tricky sometimes, but there's our result. Now if we do this again to look at the sum of 10 terms, well really we just want to compare if anything is any different. So we can plug in our values. First term's the same, ratio also the same. This time our exponent's 10 for 10 terms, minus 1, and then again 1/3 minus 1. And what you'll notice is you still get 71, but now your decimal is a little bit larger. Okay, now your decimal is a little bigger, but again, still 71. It's just closer to 72. Interesting. Let's see what happens if you take 50 terms and add them up in this series. So again, your formula is the same. T1 Rn minus 1 over R minus 1. That'll work for any geometric series. So 48 again, ratio of 1/3. This time your exponent's going to be 50. Minus 1 over that again 1/3 minus 1, and what you end up getting on your calculator, probably will round this one for you and will tell you it's approximately 72, or we'll straight up even tell you the number. So I'm curious, I didn't actually do this one earlier, so 1/3 exponent 50, I'm going to hit enter, okay, minus 1, multiply it by 48 and divide that by 1/3 minus 1, close that bracket. Okay, so it does tell me 72, which is very interesting because all of the other ones had decimals, and it was 71 with a decimal. It was really close to 72. So this one tells me 72, which is something really interesting to think about. And really dive into this and get a bit more specific on the other side. So again, if you're looking for any of these links and resources, you can find those links in the description box. Links to a blank copy as well as everything all filled in here, so you can look for that as well if you like. But if you think about those sums we just talked about, the differences between them, well, they got smaller, right? They got smaller, the differences, as n got larger. Right, so we increased the exponent, the variation between those sums went down, they got closer and closer to 72. And the sums got closer to that number 72, which is what we ended up with. As soon as we included 50 terms in that sum, our calculator said 72. okay? If you notice something about that common ratio, it was a value between -1 and 1, right? So in other words, it was a fraction in between -1 and 1, okay, which is interesting. And if you think about, and the example I usually use like in class with students is take a piece of paper, right? Take a piece of paper, and even draw you a picture, if that helps. So here's my sheet of paper, there's my rectangle, and think about cutting that piece of paper in half, right? Cut it in half. So vertically, horizontally, doesn't matter. Just cut it somewhere in half. I know that's not perfect, but hey, it gets my point across. Well, this is a half. And if I cut the other piece in half, well, that means that, oops, let's try this again. There we go. Oh my goodness, straight lines are very difficult. There we go. That means this is going to be a quarter. And I can cut this in half again, which means this is an eighth. And one more time. And you can see what happens to this pattern. That's a 16th, which means if I do it one more time, this is 1/32, so on and so on and so on. So dot, 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 because we could keep on going. But if you were to take each one of those fractions and add them up, you're going to get 1. And you can cut this piece of paper into infinitely many small pieces, but if you take all of those infinitely small pieces and put them back together, you still only get that original 1 sheet of paper. So you can add up infinitely many numbers, and they approach 1, no matter how many you add. Now, think about this sequence that we just built. I started with a half, then 1/4, then 1/8, then 1/16. This is geometric, because r is equal to a half. And you can think about taking a half, multiplying it by a ratio to get 1/4. Do it again, you get 1/8, so on and so on and so on. So this is geometric. The sequence will never stop because theoretically, I can cut that piece of paper up infinitely many times. However, I am limited by the tools at my disposal. I'm limited by the fact that scissors are only as good as you make them, right? And the smaller that piece of paper gets, the harder and harder it gets to cut it in half. But in theory, we could do it if our tools were more sophisticated. So if my ratio is a fraction, which it is this time, it's 1/2, I can do this. And my infinite number of terms in that sequence will add to one certain number. They converge to 1. The one that we talked about together, those sums and that series converge to 72. So there's a definite point at which I can add up another infinitely small piece that doesn't necessarily change what that sum is anymore. So if you think about that in terms of this piece of paper, eventually you'll get to a point where the piece of paper is so small that it's negligible when you were to add it to all of the other terms in that series. It doesn't make a big difference, right? Eventually you'll get to a point where you have 99% of your piece of paper accounted for. That 1% to include it doesn't make a large difference in the grand scheme of things. But think about a sum for a series that may look like this. Right, so think about your first term, t1's 3. Think about your ratio. Here's 4. 3 times 4 is 12, times 4 is 48, so on and so on and so on. So if you were to take the sum of the first 5 terms of this series, we can do it exactly the same way as we've done. So plug in what you know. 3, ratio this time is 4. If I'm looking for the sum of 5 terms, then it's 5. And then my ratio, again, is 4, so 4 minus 1. And the number you end up with, 1023. So pretty large, if I were to add them up. You can even take these 5 numbers, add them up. You should get 1023. If you do that for 10 terms, right, t1, rn minus 1, and then r minus 1 one more time. So there's your 3, there's your ratio. 10 terms we're going to add up, so that ratio happens 10 times. And then 10 minus 1. Nope, the ratio is 4. I lied, 4 minus 1. There we go. But what you'll notice is this is a super large number. 1,048,575. Much larger than 1023, and they are very different. And that is a result of our ratio being a whole number, not a fraction. It is going to keep on growing infinitely. The more terms I add, the bigger the number gets. Try it with 50, and your calculator might not even tell you a number. Because it will need to be written using scientific notation. That is how large that it ends up being. and you end up with a result that says 1.267, so I'm not going to round it, 76506 multiplied by 10 to the power 30, a much larger number than 1 million. So no matter what happens in this case, the more terms you have, the bigger and bigger and bigger your sum is going to get. It's not going to approach one specific number because it keeps on growing. It's exponential growth here. It does not approach one specific value. So if you notice something about those sums, they get larger and larger. And your ratio here is a whole number, right? It's greater than 1 as well. We talked about what would happen and why our ratio can't be 1, because then on the bottom of your fraction, for your summation formula, it'll say 1 minus 1, right? You'll end up with a denominator of 0, which we can't have in math, right? Division by 0 is something unquantifiable. So my ratio here is bigger than 1, which leads to that massive growth. Okay, so think about what happens then. This is really where the calculus leap kind of comes in. As we approach infinity for n can be whatever we want, but assume the ratio is a fraction. So we're going to assume that our ratio is 1/2. We're going to see what happens to values of Rn, right? We're going to see what happens if we take our ratio and apply it, give it a different exponent every time, and observe what occurs, right? Maybe that gives us a formula. So I'm going to use the values of 5, 10, and 50 again, keep them consistent. So let's assume our ratio is 1/2 once again. So if we take the sum of any 5 terms, then you've got T1, 1 minus your ratio to the power of n, in this case 5, on the bottom, 1 minus your ratio. So I switch this around. Again, we talked about what could happen in the last video if you do Rn minus 1 or 1 minus Rn. They mean the same thing, it's just different by a factor of a negative. So if you plug in your numbers, I don't know T1, so I'm going to leave it out. And let's make this a bit smaller so it fits in there. There we go. So leave out T1, you don't know it. 1 minus, let's just put the value in. So this works out to be 0.96875. That's what the brackets work out to be, over 0.5. Okay, so there's what happens to my set of brackets. It's 0.96875. That is so close to being 1. So let's see what happens if we increase the number of terms that we look at. The sum of 10 terms instead. T1, 1 minus the ratio once again. This time our exponent's 10. So 1 minus our ratio again of 1/2. And what you'll see with the sum of 10 terms is that your set of brackets gets so much closer to 1. Right, so this is what's happening to Rn. As you take that ratio and increase the number of terms in your series, that set of brackets gets closer and closer to 1. So the more terms you take, essentially that set of brackets becomes negligible, because you know that multiplying something in math by 1 doesn't change the value. So let's see what happens if we include maybe the sum of 50 terms. So T1, 1 minus 1/2 power 50, on the bottom 1 minus 1/2 again. So the sum of 50 terms, and you can even put this part in your calculator. That part we'll do together to really make this point. Okay, so there's my 1/2 power 50. Your calculator will tell you it's 1. 1 over, 0.5. And the reason being, 1/2 to the power of 50 is such a small number that it's basically irrelevant. It's basically irrelevant, right? That number is so small, you're taking 1/2 and multiplying by itself 50 times. It's so tiny that if you subtract it from something, it's basically like you didn't take anything away at all, which means that your brackets end up being 1, which means they end up doesn't make a difference anymore. So if you know you have an infinite geometric series with a ratio, okay, with a common ratio in between -1 and 1, so a fraction, well, then you know that the brackets are irrelevant. They aren't there in this formula. You could still use the other formula, but it's just more work. There's more things you need to find for it, so why bother? Right? Here's your infinite series formula that you really only need to know 2 things, the first term and the ratio. As long as your ratio is a fraction in between -1 and 1, it will approach one value. It'll be convergent. If it's not a ratio in between those two numbers, it will be divergent, and it will not approach one certain value. Okay, it'll just either keep getting really, really large, really positive, or really, really negative. But on both ends of that spectrum, you're going to have very large numbers. So let's see what you can do with this. So with that example, it says determine whether each infinite geometric series converges or diverges. If it converges, find the sum. Now it does say that this is an infinite series. It says the word infinite in there, which is important. We'll talk about convergent, divergent. So the first thing we need here is a ratio. So I can take one term, divide by the previous term to find my ratio. The second term is 1/3. The first term is 1. If you divide them, well, there's your ratio, 1/3. I know the first term is 1. I have enough information to find out what the sum of an infinite number of terms is here. I can determine where they're going to converge using this, because my ratio is 1/3. That is in between -1 and 1. So I can use it. So the sum of an infinite number of terms here will be 1 divided by 1/1/3. And if you plug that into your calculator, you will find out that it is 1.5, which makes sense, right? 1 plus 1/3 already is, well, 1.333, repeating. So I'm already really close to that 1.5 value. And if you keep adding in little pieces over and over and over, 1/9, 1/27, 1/63, and you keep going, eventually you're going to get closer and closer and closer to 1.5. Okay, that's what this is trying to say. It will converge. Oh, I had to cough there, so I had to turn it down. It'll converge to this value. If you keep adding infinite terms to this, 1.5 is your best number it will make. If you think about b here, you need the same thing, so I need a ratio. I need a first term of 4, which I have, but my ratio here, if I do -8 divided by 4, I'm going to see my ratio is -2. The problem is that r is not in between -1 and 1. Therefore, this is divergent. Okay, the infinite sum will not approach one specific value. It will keep on getting larger and larger and larger and larger. Because that number is not a fraction, think about doing successive powers of -2. The number will keep getting bigger and bigger and bigger. Right, there's my ratio. If I put it to a power of something like 10, gets quite large. If I do that ratio again, and I even put, maybe 50 terms like we talked about before, that is a very large number for scientific notation. Okay, so this is divergent. It does not approach one given value. Think about example 2, last one here. So the infinite cases are very, very nice because of how short they are. First term of an infinite geometric series is 2. Well, that's good, that's T1. The sum is 4. That is saying the sum of an infinite number of terms, because this is an infinite series. That means if there is a sum, it converges to 4. Right? That is what the sum will be of an infinite number of terms of this sequence. Our job is to find the ratio. Now, if it converges, I know the ratio should be a fraction. That's by definition. So let's see what we can do. Your formula is the sum of an infinite number of terms, T1 over 1 minus r. I know a couple of these things. The infinite sum is 4. The first term is 2. Plug in what you know, and it turns into, well, a solving equations type problem. So 4 equals 2 over 1 minus r. Now you can cross multiply here. So you can take 4 and multiply it with 1 minus r, and that should be equal to 2 times 1. There's no value underneath the 4. 4 is a rational number. You can write it as 4 divided by 1. So 2 times 1 is 2. Multiply your other cross product, and what you'll end up with is 4 times 1 minus r is equal to 2. However you choose to solve this is up to you. I'm going to divide both sides by 4 here to cancel the 4's so that 1 minus r is equal to 1/2. You can get the r to the other side. Let me get rid of this box at the bottom. Give us a little bit of space here. Clean it up a bit. There we go. You can do this a couple ways. You can add an r to both and then subtract the 1/2. You can do both of those at the same time. So 1 minus 1/2 is going to leave you with 0.5, which is your ratio. So it's probably a little better to leave it as a fraction. There you go. There's your ratio of 1/2. Which brings us to the end of our playlist on sequences and series. We talked about, a common difference or arithmetic cases. We talked about a common ratio, our geometric cases, and we talked about what happens if that sequence or series never ever ends and it goes on for infinitely many terms. So we got all of the things in there. What we'll do next is we'll talk about quadratics. That'll be our next unit. So look back for those videos as well. So I hope these help. And until next time, have a wonderful rest of your day.